Here's part 2 of the topic. So the standard error is larger when meaning the means of the possible samples are more spread out and less accurate, when the sample size is smaller, or the population standard deviation is larger, meaning when the population members are further apart from each other. Because when the population members are further apart, the sample means also become further apart. So here's an example of what I mean. Here's an example in Excel. I just made up this demonstration. Here we have population members of 1, 4, 7, and 10. The population members are 1, 4, 7, and 10. And over here, we can see all the possible samples of 2, and their sample means right here. Here we can see all possible samples of 3, and their sample means. We also notice that these are further apart, and these are closer together, like we talked about before. If I change the population members over here to become 1, 20, 40, and 60, these numbers will be more spread out than they used to be. So the standard error of this set of numbers will go up, and for the samples of 2, and these numbers are also now further apart than they used to be, so the standard error of these numbers will also go up. So this standard error and this standard error both went up because the population has more spread. Because when the population members are further apart, the possible samples move further apart from each other. So this standard error up here is still larger than this standard error down here, but both standard errors went up compared to what they used to be. So that's what I mean when I say the standard error goes up when either the sample size is small, like a sample size of 2 instead of a sample size of 3, or when the population has more spread. So here's another example with that formula. If the population size is 50, if the people in the population have a standard deviation of 4.5, and someone actually calculated the means of all possible samples of 10, what would the standard error equal? So what it's asking for is just, if we have a population size of 50, a sample size of 10, and the population members have a standard deviation of 4.5, what's the standard error for all the possible samples of 10 that could be selected? Well, it would just be with this formula right here, doing the same thing the same way we did it before, and it comes out to 1.3. Here's an example with the different population size. So now, instead of the population having 50 people, it has 100 people, and this would now be 1.3. So I need to double check this for a second. 50, 10, and 4.5. Oh, so they come out to about the same. Just when you round it, they come out about the same. Here with the population size of 200, so these two stayed the same, but the population size went up to 200. It changed a little bit. It would take a lot of work if we wanted to do this a long way, because we would have to actually sort out the population into all possible samples of 10, and there would be a lot of them, and we'd have to get the mean of each one, and then calculate the standard deviation. So if the population size and sample size are really different like this, it's too much work to do it the long way, but the formula will do it for us. It was easy to do it the long way back when we had a sample size of 3 and a population of only 4, because there were only 4 possible samples. Now let's talk about this right here. This part of the formula is something called a finite population correction, which means this part of the formula actually only has to be used when the population size is small. And I'll tell you what I mean by that. If the population is actually much bigger than the sample size, like how it is in most studies, this part can actually be left off. And this is actually the standard error formula right here. Generally, if the population is at least 20 times larger than the sample, this part can be left off, and this would be the standard error formula. For example, if the population size was 600 and the sample size is 20, this part could be left off because that's 20 times bigger. So the reason why is because when the population size and sample size get further apart, this part of the formula actually gets closer and closer to 1. See how when the population size keeps going up higher and higher, right here, it gets closer to 1. And remember, when you multiply something by 1, it doesn't change the answer. So if this comes out to about 1, like 0.97, it's really not doing anything, so it can just be dropped off. This is the short formula for if the population is 20 times larger than the sample size. So here's an example. If we had a population of 200 people, that population has a standard deviation of 4.5. And we're talking about the means of all possible samples of 10 people. This population size is 20 times larger than the sample size, which would mean that if we used both formulas, we would actually see that they both give about the same answer. So it really doesn't matter which one we use in this situation. Now, if the population size was 1,000 and the sample size was 10, they would come out really close because the population size and the sample size are really far apart. So they get closer to 1, and if the population size is about 20 times larger, you can get a fairly accurate answer with just the short formula, meaning the short formula and long formula are about the same. Now we need to talk about something called a z-score. Every sample mean in a sampling distribution has a z-score that shows the number of standard errors the sample mean falls from the population mean. And I think this will make more sense once I show an example right here.